Today, the beautiful scenery of the British Isles seems far removed from the catastrophic events that shaped it in the past. The tranquility of these cool running streams and flowing waterfalls in County Antrim provide a wonderful escape for local people and visitors to relax and pass the time. But as we contemplate the slow processes that can be observed going on today, we're faced with important questions about the dates that geologists apply to the rock layers. Haven't sophisticated dating methods been developed that demonstrate conclusively that the Earth's rock layers were deposited over vast ages? The most widely used geological clocks are based on the decay of naturally occurring radioactive isotopes in rocks and minerals like these. An unstable parent isotope decays into a stable daughter isotope. This decay process is used to estimate when the rock or mineral sample in question was formed. However, in all of these methods, it is necessary to make some assumptions, in particular about the starting conditions, the rate at which the decay process occurred in the past, and the history of the sample being dated. This candle helps to illustrate the point. Imagine we wanted to know how much time had passed since the candle started burning. We could work it out if we knew certain things. How long the candle was originally, how fast it had been burning, and whether or not it had been tampered with. Likewise, in order to date a rock, we need to know how much of the daughter isotope the sample contained in the beginning, how fast the parent isotope had been decaying in the past, and whether the amounts of parent and daughter had been altered by any process other than radioactive decay. We can verify our assumptions provided a human observer is present. But when dealing with rocks that formed in the past, we usually have no way of knowing whether our assumptions are correct. In fact, many lava flows formed during recent volcanic eruptions give very old dates by radioactive methods, revealing problems with the standard assumptions. One of the best-known dating methods uses the radioactive isotope carbon-14. Carbon-14 is commonly used to date samples of wood, shell, or bone. However, carbon-14 decays very quickly compared to some radioactive isotopes. So quickly, in fact, that any samples that were truly millions of years old would not contain any carbon-14, because it would long since have decayed away. Nevertheless, measurable amounts of carbon-14 are routinely found in samples of fossil materials, including coal and oil, causing us to question whether these samples are anything like as old as most geologists assume. Some have tried to avoid this conclusion by claiming that the carbon-14 must be due to contamination, perhaps when the samples were handled and processed in the laboratory. However, the technicians in dating laboratories meticulously clean such samples with hot strong acids and other treatments to remove contamination, and yet the samples still contain measurable amounts of carbon-14. Other processes point to much younger ages than most radioactive dating methods. Consider, for example, the accumulation of salt in the oceans. Rivers and other sources transport more than 450 million tons of salt into the oceans every year. Only a quarter of this salt leaves the oceans, and the rest simply builds up over time. Even with the assumption that the sea had no salt to begin with, the present amount could have accumulated in less than 42 million years. But the oceans are presumed to be over 3.5 billion years old. Of course, the amount of salt entering and leaving the ocean may have been different in the past. However, even the most generous calculations have been unable to explain why the oceans are not much saltier than we observe today. Another well-studied process is the accumulation of sediment on the ocean floor. Most of this sediment is transported into the ocean by rivers. Estimates of how much sediment is carried into the oceans vary considerably, but a conservative estimate is about 20 billion tons per year. At this rate, the oceans could have been filled with sediment 19 times over in their presumed long history. In fact, the sediment on the ocean floor averages less than 400 meters thick, causing us to wonder why so much of the expected sediment is missing. Perhaps some of it was recycled by tectonic processes, but it's difficult to see how that could resolve the discrepancy completely. The rate at which the land is being worn down is also a problem for conventional dating. Geologists estimate that a continent like North America is being eroded by water and wind at a rate of about 60 millimeters every 1,000 years. That means about half a centimeter of material will be eroded from this rocky landscape during an average human lifetime. Measured in this way, the erosion rate seems very slow, but it suggests that North America could have been worn down to sea level in only 10 million years. According to the conventional timescale, the continents have been around for over 3.5 billion years, and in that period, the continents could have been completely leveled more than 340 times. Rates of erosion are even greater in areas of high topographic relief. High mountain ranges, such as the Himalayas, are being eroded at a rate of about 1,000 millimeters every 1,000 years. With such high erosion rates, it is reasonable to ask how mountain ranges, believed to be hundreds of millions of years old, could have survived to the present day. Even with a very low erosion rate, no continent should have remained above sea level after a few hundred million years.